This is video number 2 for section 5.7, solving equations involving e or natural log. We're just going to revisit a couple of the types of equations that we've been solving and integrate in this new material. So let's start off with exponential equations. Certainly these have been the most important type of equation that we have solved in chapters 4 and 5. An exponential equation just means an equation where the x is up in the exponent position. Well, here's an example of one. The only thing that looks different from what we've done before is that the base of this particular equation happens to be e, our new special number e. Well, other than one small tweak, I'm basically going to run through the same steps that we've been doing for some time. How do we solve exponential equations? Well, step 1 was take the equation and put it into exponential form. Exponential form means one base, one power, one result. That means I have a couple of pieces of junk in my way. The 6 is in my way, so I'll need to deal with that. And then the 4 is in my way, so I'll divide both sides by 4. And now my equation is in exponential form. A base raised to a power equals a result. Well, step 2 that we've been doing in this chapter is take the log of both sides. And when we've been saying that, we have meant log, log base 10. We've been using that because it's on our calculator. Well, now we have two choices on our calculator. We could use log, or I can use ln, the natural log. And as you'll see in a moment, if the base is e, there is a slight advantage in using ln. So let's take the ln, the natural log of both sides. That's as simple as writing ln in front of the left and ln in front of the right. Why would I do such a thing? Why would I introduce logarithms? Well, for one and only one reason, and that is step 3 because of the power rule, right? The power rule works for natural log just as much as it does for any other log. That's that great rule that says that if you have the log of a base to a power, the power can come down front as a multiplier. Now the x is down on the main line. I'm going to be able to isolate x. One small thing before we get to that, and this is why the ln turns out to have an advantage. This part here in the middle, the ln of e, well, that should look familiar. We worked that problem in the last section. Remember that I can insert an understood base e right here. This says log base e of e. In other words, what power do I have to put on top of an e to get an e? Well, that would be a 1. E to the 1 power would be e. This green box, therefore, is just equal to 1. Multiplying by 1 doesn't really impact anything, so I don't need to write it anymore. Well, we're almost done. The final step is simply to isolate the x. I can do that with a couple of quick, simple algebra moves, right? Subtract 1 from both sides. Remember that ln 17/4, that's just some exponent that I could get from the calculator. I just don't want to get it right now because I don't want to round in the middle. And then divide both sides by 3. And there's my final exact answer. Of course, what I generally want is a decimal approximation, and this is ready to go for the calculator. Now be careful when typing it in. You might want to do it in pieces. For example, you might just want to type in the numerator, hit enter, and then type divided by 3. If you're going to try to do it in one step, you're going to have to put an extra set of parentheses around the entire numerator before you hit by the divide 3. In either case, what you should end up with is x is approximately 0.149. Remember, while the ln looks a little different, it is just a logarithm. We worked this problem using the same set of steps that we have been using for some time. Let's go on to the second type of equation that you will see, and that is a logarithmic equation. We've solved several of those in chapters 4 and 5. That just means an equation that has a log in it right from the start. In particular, this equation, and the kind that you will see on the homework, this equation has a couple of ln's right in it, a couple of natural logs. All right, the first step in solving a logarithmic equation has been to put the equation into log form. Log form means one log, one base, one result, and one power. Right off the bat here, I can see I've got some problems. I've got two logs. That's an issue. Now I am noticing there's a subtract in between, and it makes me think of that rule about the subtraction problem of two logs. But before I get there, the other thing messing this thing up is this 2 sitting here in the front, this multiplier of 2. I can't use that subtraction rule until I deal with the 2. Now maybe you're thinking, well, let's just divide everybody by 2. And that would be a great suggestion if there was only the one log. But if I divide everybody by 2, then this log would also have to be divided by 2. That would create a new coefficient sitting in front here. So that's not going to help me. The only thing I can do is to use the power rule in reverse. So normally we take our power and we move it to the front. In this case, I'm going to take that multiplier in the front and put it here as a power. Now you have to be careful that power of 2 that we just moved up there applies to everything that was sitting there. In other words, I now need to square 4x cubed. Well, 4 times 4 would be 16. X cubed times x cubed would be x to the 6th. I guess another way you could think of it is I distributed the 2 to the 4. 4 squared is 16, and I distributed the 2 to the x cubed, 1 base and 2 powers, multiply the powers. We'll copy down the rest of our equation. Well, now that I've dealt with that coefficient, I do have a subtraction problem of 2 logs. So I'll use another one of the famous 3 rules of logs. We used the power rule in reverse a moment ago. Now I'm going to use that rule that says if you have a subtraction problem of 2 logs, that is the same thing as a single log where the result is the quotient of the 2 previous pieces. Let's see, let's check that. The log of a division problem is equal to the log of the top minus the log of the bottom. So I think we've done that correctly. This expression we've got here can be simplified. Let's go ahead and do that. The 16 and the 8, of course, simplify to 2. And then I can use that rule of exponents where I leave the base on the top and I subtract the powers. Now this equation is in log form. It's got one log, one base. You say, where's the base? Remember, it's there. It's that understood e. You can always write the understood e for natural log. One log, one base, one result, and one power. Why do we put these equations into log form? Well, we do that for one reason, so that we can then switch to exponential form. Remember, at the moment, our x that we're trying to solve for, that we're trying to get by itself, it's trapped in this logarithm. It's been trapped in these logs ever since we started. Well, we're going to free it up now by switching to exponential form. That's that semicircular pathway idea. And that is going to give us e to the 5 equals 2x to the 4th. The x is no longer trapped by a logarithm. Well, I should be able to finish this off pretty simply. I just need to isolate x now. The first thing I can do is deal with this 2 by dividing both sides by 2. That gives me x to the 4th equals e to the 5th over 2. The x is almost by itself. The only problem is this 4th power. Well, I can undo that with the reciprocal power, the 1/4 power. So if I raise both sides to the 1/4 power, I end up with the exact answer, e to the 5th over 2, all raised to the 1/4 power. Now we can go to the calculator and get a decimal approximation for this answer. And I get x is approximately equal to 2.935. Be careful when you're putting this into your calculator. You're probably going to need the parentheses around the e to the fifth over 2. Remember that e to the x button? You're going to use that button. And then some of you may also need a parentheses around the 1/4 to get it to come out right. Other than the look, nothing has changed. We put our equation into log form so that we could convert to exponential form so that we could isolate the x. It's the same series of steps that we've been using. This is a great section to end on because you're going to get to revisit some of the very important types of problems that we've been doing. Sure, things look a little bit different, but the essential steps remain the same.